Thank you so much to our speaker. And our next speaker is Angjoo Kanazawa. Angjoo is an assistant professor in the Department of Electrical Engineering and Computer Science at the University of California. See to act, act to see. Just make sure. The switcher of a warm welcome.
My outfit is what?
Make sure that the output sets on the headphone jack.
Oh, okay. How do I do that? Like settings, sound,
So
output, headphone jack.
headphone jack.
Okay,
Perfect.
good. Okay, good. And then here we go. Awesome. Okay, all right. Very exciting. Thank you for inviting me here. I think I've been doing a lot of 3D vision stuff with motivation with robotics, but my group is really trying to do more robotics thanks to my students. And so it's really exciting to talk about this because we just put this on archive. Okay, so from this title, I think you should be thinking about this Gibson quote. We perceive in order to act, and we act in order to perceive. And the kind of vision background that I was kind of raised in, this was really the ultimate goal of why you want to do perception. And it's really exciting because I think the time is really ripe, I think, to do this type of research. And so this paper, this is not even archived, it's coming out today at 5 p.m. Pacific time. And this is a paper called EyeRobot that I'm just gonna talk about. Okay, so one day my student Justin, who is the lead author on this thing, says, Angjoo, I want to make an eyeball. And I'm like, okay, sounds cool, just do it. And then he actually went and built an eyeball, and it was like over a long time period. In the beginning, it was like for him to figure out how to kind of put a little robot together, which is a really great learning experience. And that really got to this project in the end where we really wanted to train this eyeball so that we can achieve some task, just like what Gibson was saying. And in the end, this is what the paper is about. So here's a robot that is moving around. And we put this robot onto an arm. This is the eye view from a robot. Let me give you this picture. So this is this is the eye mounted on this hand robot. And the task is to put this towel into this bin. But when it starts, neither the towel nor the bin is in the picture. So you actually first have to look for the towel, and then look at the bin, and then put it in. So that's really the kind of the idea. If I do it again, see, it's looking in the front, and so it has to look left or right and do this search behavior. Okay, so why active vision? Simply put, when embodied, you just don't get to see everything at once. We're not omniscient. And this is actually probably a good thing because it makes us to be more intelligent. Because you can't see everything at once, not everything is laid out for you, which means you have to make a sense from the little bits that you see. And today I'm not going to talk about it, but this work called Cuter that is being presented at this CVPR is also this type of idea where you want to do online prediction of 3D as things come in. But with this is really a natural transition towards active perception because you are going to make decisions and actions that are going to maximize useful information after seeing a little bit. Okay, and we're really getting to this type of perspective because we've been working on nerve stuff for traditional vision problems. So for example, multi-view scene reconstruction, with Gaussian slots and nerves, we get these really amazing results. And we've been doing a lot of work in this space, but this may not be really always what you want. Okay, so I'm going to show you a picture, and I want you to find the Waldo, okay? All right, where's the Waldo? Yeah, are you looking for the Waldo? You found him, right? Okay, he's there. He was at that plot. But if you ask this to Claude or your favorite AI, it says, I actually don't spot Waldo in this image. And why? It's because the current architectures actually take this entire image and shove it all into this magic latents that are supposed to answer all the questions that you want about this image. Like, where's the Waldo? You know, how many Nerf darts are in this scene? 3. Okay, and so these latents have to compress everything. And so if you wanted to ask anything about it, all of it is in here, which is nice because that allows you to ask lots of questions about it. But I think when you, especially when you come to this embodied space, the space that you're gonna actually work with is humongous. And then, you know, you actually have to be like, okay, well, give me a Coke, please. So then now you're gonna look at the fridge or the kitchen. Where's my laptop? Well, then I'm gonna look for the table. Well, what if, where's my keys? Like, where are my keys? Like, it's probably somewhere here. Okay, can you please set the dining table? Then you gotta go over there. So then as you ask more and more, this kind of problems becomes obvious that it's a little too much to do. And this is really because our perception is task goal oriented. You know, you have all of these things you want to do, and that's what you go looking. And so what if we have vision models that can actively select where we allocate compute? So that's kind of what we want to do. So another pop quiz. Okay, you looked at this picture before. There happened to be something inside this. Does anybody remember? No, right? Oh, something brown. There you go. Nice. Okay, so it's hard because you actually didn't see it. Okay, so this is really the idea towards selective vision architectures. And ignoring is a very successful inductive bias. You know, we've done this a lot, like, you know, RSCNN, even transformers is about ignoring. In embodied space, the selectivity really comes in our embodied nature. The fact that we have like a face and an eye that has limited field of view, and also on top of this, nature has this foveation. ChatGPT didn't really do a very good job drawing the foveation, but that actually also selects this selectivity, which I'll get into it. But so this is a really nice study that said that, you know, humans fixations, you're always looking ahead at the things that you need to do because that's the task that you actually want to do. And here's another picture. I'm not so sure if you've seen this. That's okay. Okay, so the goal, okay, I'm going to show the video. And the goal for you is to count how many passes did the people in white t-shirt make. Okay, so let's look at this. Okay, so that's 1, 2, 3. I will let you focus. Okay. All right, so it's a trick question because I don't really care about how many passes, but did you see the gorilla that came into the scene? When I first watched this video, I didn't see the gorilla at all. Yeah. So that, look at that gorilla over there. I mean, I didn't see it at all in the beginning, right? Okay, it's because you're really focused on this task, you know? Okay, so this really can like, you know, very widely be based on what you're looking at. Your sankata patterns are very different. And the thing is, this behavior is never supervised. I mean, perhaps we can BC everything, but really it's an emergent behavior. And so how can we actually emulate this with a robot? And so that was really the goal. And so it's called EyeRobot after the movie. We built an eye and we put it on a robot. And okay, so here's the video again. But let's play it one more time. Okay, I'm gonna play it one more time. So in the beginning, notice there's nothing you can see. Okay, so now you gotta go look at left or right. Okay, this is like, you know, hopefully you're gonna put a leg on this so that it's more realistic. But okay, it first looks to the right. Okay, and then it looks the bin. The bin is not the thing you want because you first need to pick up the towel. So it continues to look. And then now it looks at the towel. I think it's excited that it saw the towel. I don't know why it does that. Now it's gonna grab it. Once it's grabbing it, now it's gonna look at the bin and wait for the hand to complete the task. So this was all emergent. We didn't supervise any of this looking behavior. The arm is, and I will describe. Okay, so the idea here is to do this type of perception loop in a sense that how to see is trained with RL. and how to train is with BC. And so perhaps this is like an RL with an RGB. I mean, it is. And this is kind of like a cycle that kind of where the gaze behavior emerges from this need to act. So like how exactly are we doing this? Okay, so Justin made this physical eyeball and he picked it up pretty quickly, which is very exciting. And so it can do these fast motions as well as smooth motions. Okay, so how are we going to train this, right? There are a couple of options. So perhaps you can do imitation, especially with inputs like area glasses. You can actually, this is our area glass and this is the gaze computation, which is actually pretty good. But you gotta then do lots of, make this, and then you also have to do the BC at the same time. I'm not so sure. I mean, that's definitely an option, but that's one way. Instead, why we wanted this behavior to be emergent so that this strategy of where to look kind of comes out through RL. But really the problem is like, what is the right environment and how do we do this? Because the problem is that if you actually have a meta area glasses, say you make the humans wear this while they perform a task, the problem is you really can't do any counterfactuals. Like what if I, instead of looking here, looked somewhere else? I don't really have the pixels for this. And so really the key challenge is that you need to do RL on top of your eye and take lots and lots of steps, but you really need the environment. The solution here was to use a 360 video. Because if you have a 360 video, actually, it's a almost perfect real to sim to real environment. Like you don't even need a renderer, especially with this given type of eyeball space. So this is Justin capturing some BC data with the tele-op, which I will describe later. So basically, we mount during training time, mount a 360 camera on the same base, and then we hear that is a tele-op the jello that we're doing to capture data. Okay, and then this is actually a simulation, manual gaze, manual operation of the 360. So really the nice thing about this is that you can actually do rendering through this thing which we call iGym, which is really just resampling of the 360 camera. And you can do counterfactual, it's like a simulation where you can ask counterfactual questions of what happens if I look there without real loss of, information. On top of this, we also emulate the biological vision by doing a foveated vision, which I will describe also, but which is also nice and efficient in many ways. Okay, so now let's learn to act. So then like, how do you do the task specification, right? Like the idea is that you want to look in a way that maximizes success, but there's many tasks, and this is again for a single task. But we decided to go with BC because it's really working well in that way. I think this can be arbitrarily different. We just wanted to kind of show that this behavior emerges for a task in which you can use BC in this particular case. Okay, so the key idea here is that the eye is from RL and the rest of the body is with BC. So the eye is free to explore, and it provides observations to the policy that is supposed to do the action, which is trained with BC. And that gives you the reward. So this is the action perception loop. So specifically, if you get an input image like this, where there's no information, I mean, you can go left or right. And so you cannot really minimize your BC supervised task. But if you actually have the right input image, then you know to go to the right to get the cup. And so this will lead to success, which becomes a high reward. Okay, so the BCRL code training loop goes like this, where the eye provides some picture from the rollout, and that picture is being sent to the robot model, which outputs some action, and the reward is really how good this prediction accuracy was. So that's the method. In the beginning, the eye is completely random, and that's what it looks like. And after about 7 million steps of PPO, it's like depending on the hardware, we didn't really have that many GPUs, so it was like a day. It converges to this policy that is, in this particular case, doing the pickup task. Okay, so this gaze behavior emerges. And so the architecture here is also foveal. So the input is the image that is being currently looking at and the proprioception of where I am looking up and the state of the arm. And the output is how to change the gaze and then action chunk as well as these value things for PPO. Okay, and so this is just sent to a big transformer where the eye transformer figures out how to move and the resulting image tokens are sent to the arm transformer. So because we were really inspired by biological vision, we are actually using foveated feature extraction. So instead of just taking this crop, we're actually taking multiple scales of the crops, but with different resolution, just like foveation. So the center crop has these all have the same level of resolution, just like foveated vision. So ones actually have the same amount, but yeah. So then this really results in like an image pyramid. And so why is this nice? Actually, there's really a neat property of scale invariance that it learns, but more than anything, it's just super efficient. Like instead of giving this image, it's 11 times fewer pixels because it's really focusing more, but incorporating the context in a low res way. Okay, and so actually this is very much like a practicality of necessity, because if you actually don't do foveation, there are too many tokens that doesn't just fit in the 24 gigabyte GPU memory. And if you actually try to match it, you can only use the 448 resolution. So the real cool thing about this is actually that the scale invariance somewhat comes up. If you are actually foveated, even though these two inputs, the scale is different, the similar patch is always going to be in different scales, right? You see what I'm trying to say, right? Like this is much closer, but like this similar patch is appearing in that one. So actually, only training on the top, you might be actually able to generalize to different scales a lot more. And we actually kind of see this behavior. Okay, and in particular, we actually do rope in a way that it actually has the same positional embedding for the same position in the scene. So this is really like Foveo architecture. Like what I'm trying to say is this particular point, like might be here, 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 and here. They all get the same positional embedding so that the transformer can figure out that they are corresponding. Okay. It's also centered, which there's more resolution in the center of your eye, which is another biologically inspired bias. Okay, so that's one thing, and action is discretized, and the continuous action for the RL is discretized, and the BC is a continuous joint space, just like Aloha. And we are not doing full self-attention on the images because that's just a bit too much and we don't have that much compute. And so really you're only doing self-attention. It's like a cross-attention between like the proprioception and the eye gaze and the images. But image and image we don't do that. That allows us to get to 60 FPS that you can actually run this. So the first experiment that we started was not a robot on this, but to track like this Boris, which is the name of this little cute bear. And we captured lots of videos. It's not like a 30-minute maybe or a 10-minute video of this Boris. And we trained to use clip reward as the clip similarity to the keyword as the reward. And you trained, just 5 minutes, just with 5 minutes of demonstration, or not demonstration, just it's video data. We did RL to look for Boris, and this is actually deployed on the real robot. And so we were testing that this RL thing actually works with the 360 camera for a while. And it's pretty snappy. It's actually able to like find Boris and track it pretty well. And here's a ablation between foveated and non-foveated camera. So if it's not foveated, it's not really robust, and it's not really can't really learn from that 5-minute video because you haven't seen all different variations of the sizes of the of Boris. But the foveated one is quite stable because of the scale invariance in the foveation. Here's some nice, okay, so we actually have some memory, as in like just repeat the past. Without the memory, when you do this peekaboo, it just like the moment the Boris goes away from the scene, which it goes, it just kind of like doesn't know what to do and diverges. But if you actually have some memory, it kind of stays there a little bit and kind of comes back. I think this is a really cool direction. We just need to explore this direction more. But right now we're just doing a very simple attention, just concatenation of like 1 second of context. Okay, so for robot tasks, we're doing these tasks like E-stop, which is to put your hand on top of this button, picking up a brush, aligning a screwdriver 90 degrees, putting a pick in place on an eraser, and then doing this like long, this is pick in place on a towel. And we do these experiments, and this is the number of demonstrations. So this is very interesting. This is my first time my students were collecting, or like I was involved in this type. It's interesting, this number of demonstrations. Yeah, it's like, it's so, yeah, I'm not so sure about this. But okay, it's good. So you collect this data. And here are some results on the e-stop where like the robot is like, the goal is to put your hand on top of this red dot, and it's like pretty flexible. The amount of data for this, I believe, is not that much, relatively speaking. Okay, and then it can actually walk around in this like big workspace because it can look. Okay, again, here's another ablation on the foveation. Without the foveation, it doesn't actually, it tend to kind of diverge and it doesn't really fixate. It's because there's more resolution at the center. So we really wanted to do a more like fine-grained task that requires the need to really have, like threading a needle or something like this. You really need the foveation. Okay, and the foveation also helps to distract ignore a distractor. So here, I mean, it's just like doesn't really know which one to go, and then kind of gets distracted. But the foveation, because this is the center bias. Okay, so foveated model is better. And let's see. Here are some tasks on the screwdriver. You're supposed to do like a 90-degree alignment to this. Okay, so our approach is able to do things on a large workstation. And yeah, here's some, this is a really cute example where if you actually free drive the arm and hold the arm, when it grabs it, it's like, okay, I'm gonna go look for the bin. But then like when it's not grabbing it, it like starts, it looks at the like, towel. So this is kind of cute. Okay, and here are some more examples now that, the towel, is on the left side, it's doing it. And I can actually even react to perturbation of the goal. Here, you're being mean to the robot, but it's doing it. And then here are some brush handoff tasks. And we need to look at this particular camera. That's what I'm trying to draw with this arrow, because look, it's like looking at you, because you're the human. And yeah, to give it to you. You see, it's like looking at the brush now, and now it looks at you. Yeah, it's following you. Okay, so I hear that the wrist camera is all the rage in robotics. And so why not do wrist cameras? They work really well, and it's like a permanent tool-centric fixation. And you can really think of the eyeball as like a wrist camera that can actually search. And it's kind of like, I think we think that the wrist camera works well because it's kind of like biased in like Caltech 101. Everything is like cropped. Then it's like easier to do the task instead of having to search. And so the fixation allows you to narrow your visual distribution. We did do baseline experiments with the wrist and exo cameras. But another nice thing is that the wrist cameras, you have to mount them on your wrist. Okay, maybe, if you're a robot person, I'm curious about your, your opinion on this. I mean, you could put like cameras on your fingers, why not? But I think it's really like if you didn't have to mount it, then your form can be lighter. But I'm curious to hear your opinion on this. But we did do this experiment where we put an external camera that could see the entire workspace, as well as this wrist camera baseline. And of course, the wrist camera can't search. So then if it's not in the view, then it fails. The XL camera lacks precision, so you can't do these tasks like putting it on the thing. Interestingly, the wrist and XL we thought would do well, but it doesn't always do well because it's just like you have more tokens to deal with, and in this particular architecture, it didn't work as well. Okay, so limitations, there's lots of limitations. We get this type of non-stable eye motion that I was saying, which I'm saying that it's excited that it found this thing, but there's no incentives to stay static. It can do these, when the training data is not as much, it learns to do blind grasps, which is actually, I think is okay. Like if you know that it's there, you don't even need to look at it. And this is actually a cool emergent behavior. It goes away when you put more data. And it can always hack because, Boris is held by a hand. It's only a single camera, so it doesn't have a depth perception. This is like Alyosha. It would be hard to pour wine into a glass. So that would be nice to have stereo cameras to do this. I can certainly, it's not 100% success rate, and it can fail to search again sometimes. Okay, so future directions. So how many time do I have until 5 to 10 minutes? Okay, great. Okay, so we actually tried to do this. The thing is, you can use any data. So you can actually go on YouTube, download 360 videos, and then you can say clip of person, and then you can actually train your RL to look at faces or feet and such things. We actually did some preliminary experiment on this where we can do like a dino vector based on query. So you take a random dino vector and tell the eye, look for this particular thing. And now when I play the video, like it looks at, that's actually the right place. That one, now it goes over here. And so you can actually use all of the internet 360 video to pre-train this. We didn't use it, but you could. We are doing a very, very simple form of memory. I think this is really interesting direction. It's also very related to Cuter, of how keeping a better state and memorizing things. Okay, I also had a baby a year ago. And so look at this baby. She learned how to walk. This is she just walking around in our office. And look at this. She's just like free roaming. And she's just like looking, and she's just kind of curious about things and moving around, walking. So I think this is a really exciting time to revisit Deepak's paper, like the curiosity. I'm telling all my students to read it again. I think this is like the right time, it's like 2017. It's a great time to revisit this. Of course, right now, it's only 3DOF, really what you want to do is put this on mobile robot, and have 2 eyes. Okay, so that's the eyeball. And speaking of humanoids, so we have another paper so this is like a video that I used to show during my job talk. It's like, oh, we want to be like this baby. Look at this baby is imitating this video. It's clearly understanding 3D. We finally is getting there. This is a work called VideoMimic that we just put out on the internet like a month ago, where I think this is the first demonstration of a humanoid walking around free train on campus. It's a zero shot, the real sim to real transfer. I don't really have time to talk about this too much. But a key, for example, okay, so this is a VideoMimic. Oh, Hongsak is here. Hongsak, I saw. Okay, here we go. That's Hongsak. Hongsak is one of the authors. This was a really big effort for co-star authors, Anthony Changming and the professors. We use all of our monocular 3D human reconstruction methods to reconstruct both the scene and the human, thanks to Megasam, and then advancement in SLAM approaches. We can actually get quite a reasonable environment now, and then we reconstruct humans to it. And then we actually don't use this, but our real to sim pipeline also allows you to do an ego view rendering. So if you wanted to do RGB sim, you can use this particular way to do real to sim. So one, I think, cool idea actually is our title is Visual Imitation Enables Contextual Control. Like, what does contextual control mean? It means that the robot figures out how to interact with the environment given a very simple instructions like the root direction. So this one is like a one long video. The only input it has is joystick. It says it goes back, it sees this like chair, so that's why it sits. And if there's a staircase, it goes up. And there's no button that says, okay, now do a walk up motion or walk down motion, or nor do we actually give in like joints to actually say what to do. It's basically figuring out what to do based on the environment. The environment is being sensed by an 11 by 11 LiDAR map. But the whole point is that you're actually letting your policy do everything. And so this is the difference from deep mimic or goal conditioned, the PHC or pulse kind of things like this, which requires these like references that says what your joints should be. The thing is, if you wanted to make this walk in the wild, you don't really know what joints it should be doing. And therefore, we replace that like goals, like these per joint goals with this just direction. And that's why we call this a generalist policy that actually can figure this out. And I think this is a cool direction. That's why we're calling it a contextual control. So that is VideoMimic. The robot does look a little bit inebriated, but this is the first time that it's walking around. And you know, our first author, this is great. I encourage my students to take long vacations. But then he took the vacation before the supplemental. So if he had another week of supplemental, I think the robot would be already walking less like that. But let me show you some exhibit. This is the first video when my baby learned to walk. Okay, first steps. And she's very excited about that. Okay, so that's January 26th. Okay, now she was like walking around by herself for a month inside and actually getting pretty good. And here's another video. This is the first time walking outside with shoes. And look at her step. This looks very much like our Shivan, especially doing one of our developments. I sent this. And it took her a month. Well, first of all, she's already walking pretty well inside. This was like a sim-to-sim transfer situation because she's never done on the shoes. Like, it feels different. And a bonus, it took her another 2 months to be able to run down a train. Okay, and this one I'm just showing it because it's a cute video. Okay, all right. So if I have time, a baby does more. Baby does more than just watching and walking. Look at her. She's trying to stab the strawberry with this lemon. And it was a very hard lemon. So I was like, that's actually quite reasonable. This affordances. But of course, you know, we want to do visual imitation, not just for walking, but for manipulating objects. This is a good video. I was trying to get this actually, but she had to be like older, and it took her a while for her to imitate this. This is like the direction that we've been doing with NERF, where we like, you know, scan the scene and then you group the objects. In order to do real to sim of manipulatable things, you really need parts. I will skip the details, but there's many different ways to group this. I mean, is this a watermelon or is that whole thing is a watermelon? You have to actually allow for both things based on the task, which we do with the scale. This allows us to reconstruct these parts from my table and do a super simple real to sim in Blender, just throwing things around. With these parts, we actually did this project called Robot See, Robot Do, where you show how to use it and then enable the robots to do the same by moving the parts. The way we do this is you scan the object, you use that, and then you have a monocular video of the demonstration, and then you segment the 3D, or reconstruct it in 3D, get the parts, use Dyno to track it in video. This recovers 4D reconstruction. Now that you actually have the 4D SE3 motion, you can use that to plan your robots to induce the same part motion. Okay. So really the key innovation was to do 4D reconstruction. Once you have the 4D reconstruction, you can solve for, you know, robot actions that results in the same motion. The cool thing about this approach actually is that it doesn't assume any kinematic skeleton or anything. So you can actually take out these free-forming things. So it's not articulated objects, it's a movable object. And then you track jointly by robots, and another message that this is object-centric. We actually use hands to figure out the action of attack, but you can actually do this for, it's not really that, you don't want to imitate the hand, you want to imitate the effect that it has on the parts. Okay, so this is great, but we have a follow-up work because 40 is still really hard. The optimization, when there's like a long video with like lots of hand occlusion, it drifts away, and see this bulldozer explode after a while. Okay, and so we really need priors. So now we have a paper called Predict, Optimize, and Distill. This is kind of like a self-improving cycle. You can kind of think of it as like a star in like the language domain, where you're constantly training a feed-forward network based on your optimization, so that it gets better and better, and the optimization gets better because the initialization is better from the feed-forward. Okay, I'm gonna wrap up. But the last message is that we're really into making useful tools. So Nerf Studio is from our group, which is what we were using to get all of these 40 reconstructions. There's G-Splat, and it's used in many different places. Here's an Amazon view in 3D is actually using G-Splat to get these furry things. But I really want to push for Visor. And if you're a student, have you used Visor in this room? Who's using Visor? Okay, there's few. All right. Okay, the Visor will change your life. Okay, so the Visor is a web-based 3D visualization. So it's not, you don't need to be tied to your computer anymore with OpenGL. You can just put it on, it's like a website. You can really change your GUIs. It's really easy to customize. This is what the Nerf Studio viewer is based on. Brent, who did this, who is actually here at this conference, is a great software engineer. It has really good principles behind the code. You can use it for Nerfs or point cloud or the human body, simple body model. The exciting thing is now we are actually combining this with robotics. So here we wrote this. This is another tool that I'm going to talk about next. Quickly, it's Pyroki. Here, this is we're using Visor as an interface to Isaac Gym. And Arthur said that this was really a groundbreaking thing, that you can actually look at what the robot is doing as it's doing a rollout and easily change this. And here is Visor as the Mujoko interface. And here's some examples when we were developing VideoMimic. We were using these things to debug. This is directly from the computer on the robot to Visor. You're running Visor on the humanoid. You can also use Visor to release your websites. All of our results are, not only us, other people do it too, using Visor to do interactive reconstructions that are very exciting. And then you can generate shareable links. So you can do your visualization and then click a button, and then you get a URL, you send it to your advisor, and then their advisor gets to see the results in 3D or 4D. Okay, lastly, this is the latest thing, which is PyTorch for any type of robot kinematic optimization problems like inverse kinematics and the motion retargeting. It's basically just JAX-based way to do this. The nice thing is it really uses the right implementation of the Lie groups. It's super easy to add new costs. It's cross-platform. And it uses Levenberg Mark I to solver. So this is such a great solver. For this reasons alone, you should use this optimization framework. CPU, GPU, it's really simple, and it's an open source. It's faster than Kurogo. So please use this and contribute. It's an open source project. It's also in Visor, so you can look at it. And you can tune your cost as the robot solves this. You can do all of these things. And this is actually what we use to, you can do hand object retargeting. You can do retargeting on human bodies. And this is actually what we used for VideoMimic. Okay, all right. So thank you. Really, in closing, it's an exciting time to revisit active perception. And we have really great tools, so please use them. And really, really big thank you to my group and my collaborators, because this is really their work. And I will take any questions. Thank you.
Some awesome talk. So my background is neuroscience, and I really like the foveation part because I think it's been just generally ignored in computer vision, and people will say, "Why would you want to throw away information?" I thought that was really cool, and the application to robotics. I wonder if you've seen or run experiments where the transform is based on eccentricity. So yeah, you preserve the foveated high resolution, and in the periphery, you gradually adapt the current width of the Gaussian filter. Have you done experiments?
So that's basically how it's implemented, actually, because if you do the multi-scale, it's just it gives highest resolution to the center, and it's like actually literally like how the fovea is presented.
Okay, but do you re-render the image in like a spatially adaptable way where
it's resampled, right? It's resampled by linear sampling. So that's basically like your Gaussian filter. We don't necessarily like filter it, but
okay. Yeah, I was curious because sometimes like it does give certain effects.
Yeah, that would be exciting to try actually. So it would be easy to do.
And have you seen other ways in which it's helped robustness? Because I thought that was really exciting. Sample efficiency, but I wonder what other things.
Yeah, that's by the scale invariance. I actually think is a really exciting part of this. One of my first papers is scale invariant neural network, which is that you don't really want your network to really relearn the same features for different scales. This one, you're actually kind of solving it at an embodiment stage, basically like, basically what I'm saying is you can train on only the data that looks like the top, but it will generalize to the data that looks like the bottom because of the foveation. Yeah, and actually this is very interesting. We also implemented with the rope so that it is kind of like the foveation. This one is kind of like it's like a positional embedding thing. Instead of just treating it as a normal pixel, the pixel location is actually relative to where it is. Yeah, and this actually also makes a difference, I think. We didn't ablate it exactly because it was earlier on, but yeah.
Thank you.
Thank you.
So I have another question about the foveation. So I thought it was really interesting how it was kind of like looking around. Do you think that's sort of a failure of it to stabilize, or do you think there's some sort of significance to that? Because like humans actually do like microsaccades.
Oh yeah.
Might be related.
Yeah, that's true. It's possible that the microsaccades are actually useful behavior. It's really interesting. It doesn't seem so consistent to me. I think it would be a good question to ask Justin more because when it really likes to bounce sometimes, but then sometimes it's like not, So I guess it could be emergent in that particular way, but yeah.
Yeah.
Cool. That would be cool. Thank you.
What other policies have you considered for paying attention to this foveation besides just RL? Because you can do very traditional stuff like feature tracking rather than reinforcement learning. I'm assuming you want to generalize, but like different tasks will probably benefit from different sort of reward function, but are alternatives to just RL and then task-specific reward function?
Okay, so the nice thing about this is actually it's not really task-specific reward function because it's actually about performance with respect to the task. So that can be anything, and then you can just directly use it. So in that way it is. But also I didn't really want to do the BC teleop. That means you actually have to do a joint collection of the eye gaze as well as your demonstration. This allows you to really disentangle that, and that's really the data collection. The need to not have to do the data was one of the reasons.
Thanks so much for the great talk. One question for me. So in this case, you're showing a robot that can change the location of the camera. Do you see the same concepts applying to an embodiment that has fixed cameras in the sense that you end up selecting the relevant tokens?
I think that's the kind of idea that we would like to do, but it was kind of hard. I think this is like past foveation ideas. I think it's just that when the task is really about classification or segmentation. Perhaps it is useful to do the selective thing, but I think it's really hard to show because you can already do really well by cooking it. So I think this is why it's like nice, guys. I feel like active perception really requires a large workspace to show that it's necessary. This is why in VLMs, you are actually using that magic latence, like, you know what I mean?
Yeah.
And I think there's definitely a case there too. You don't want to do that magic latent push everything
slow.
because it's slow and it's not really like good allocation of performance.
Yeah.
But like, you know, maybe it's like simpler. You don't need to, and it's okay. But that's because you're trying to do everything like here.
Yeah.
Yeah.
That makes sense. Thank you so much.
Great, thank you.
Hi, very good talk. And about another question about the first, the foundation work. Very interesting, very creative. But as an end-to-end roboticist, right? I take beef with, you know, treating the high as a different degree of freedom than any other degree of freedom of the robot. Right?
Okay, yes.
You know, if you know, I'd say I optimize a high-level reward. If my robot needs probation, this will automatically emerge from the data, right? If I collect enough RL demonstration and what, either demonstration or reward. So how to convince an end-to-end roboticist that this is actually good thing to do? Treat high differently than other things.
Okay, so I think this is like, I think if you're end-to-end roboticist, this is very easy. You just don't treat it differently and just do RL and everything will emerge. I think this was kind of more like people who are addicted to BC. It's more like, hey, you can take a step towards not having to collect all of your data and have these behaviors emerge, but still use it as a task specification. So I think this is kind of like, ideally, you don't do any of this and everything emerges. And so then there wouldn't be any specification. But I would think of the BC as really more just a task specification. Like even in the RL case, you have to specify the task in. It just happens to be in this way. That's my take. Thank you. Okay, great. All right.
Awesome. Thank you so much.
Thank you.
And yeah, let's give a round of applause to that.